Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will continue with Chapter 8, Part 2, Alcohols, Ethers, and Thiols, specifically talking about why they have the properties they have. Okay, so when we introduce the alcohol, we introduce the functionality of carbon bonded to oxygen bonded to hydrogen, okay? And when we talked about electronegativity, we found that we had nonpolar and polar bonds, okay? In the case of the alcohol, there is a polar bond between the carbon and the oxygen and a polar bond between the oxygen and the hydrogen. Therefore, we have a partially positive carbon, a partially negative oxygen, and a partially positive hydrogen. Okay, if we look at the electron density map of this, the negative area is shown in red here. So the lone pairs on this oxygen account for the higher electron density in those areas, and the fact that we have those polar bonds creating a pull toward that oxygen here means that the hydrogen is partially positive as well as the carbon being partially positive. Okay. This partially positive, partially negative bond here leads to a new type of bonding we haven't discussed until now. That is called hydrogen bonding. Most alcohols associate in the liquid state by hydrogen bonding. So because there's that polar bond between the partially negative oxygen and the partially positive hydrogen, that means that that hydrogen wants to go and share part of its positive charge with nearby electronegative atoms like oxygen, nitrogen, and fluorine. While this bond is not as strong as a covalent bond, it's only between 2 and 5 kcals per mole. And most of covalent bonds are higher than 100 kcals per mole. This hydrogen bonding, because of the number of times that hydrogen bond, can significantly impact the physical properties. So up to now, we were looking at molecular weight, and the shape of the molecule changes the physical properties of alkanes. They only have that London forces or those dispersion forces holding them together. So the longer they are, the more dispersion forces they have. Here we have the ability for that hydrogen to hydrogen bond with neighboring partially negative atoms. So in the case of ethanol here, we actually show 4 different molecules of ethanol, all hydrogen bonding in a couple different ways. We have, in the case of here, the hydrogen is bonding to the partially negative oxygen, and the partially positive here is bonding to this oxygen. So that accounts for a couple of the hydrogen bonds. But we also have the hydrogen on that oxygen that can hydrogen bond to a neighboring electropositive, electronegative atom like oxygen. So for every single molecule of ethanol here, it's bonding 3 other times to create this immense network of hydrogen bonding. And all those little additions of 3 and 5 kcals per mole add together to significantly change those properties. So let's look at a table here. And before, when we were looking at hydrocarbons and dispersion forces, we were looking at how molecular weight more significantly impacts the boiling point than anything else. Here we see a change. If we compare ethane to methanol, they have approximately the same molecular weight, but there's almost a 75-degree difference in the boiling point. And there's a difference in the solubility in water, okay? Because methanol can hydrogen bond, it can also hydrogen bond to water. That means that instead of being insoluble in water like ethane would be, it is now infinitely soluble in water. Okay, let's move up 1 carbon more to comparing ethanol and propane here. They have, again, approximately the same molecular weight, but they have almost 100-degree difference in boiling point. And ethanol is infinitely soluble in water, and propane is insoluble in water. So the hydrogen bonding is accounting for not only the boiling point, but its solubility in water. And we go up 1 more carbon here, and we see that there's, again, a 100-degree boiling point difference, very little difference in molecular weight, very big difference in solubility. Now at this point here, when we add that next carbon to get to the butanol, we'll have 4 carbons and 1 group that can hydrogen bond. we start to limit the solubility so that hydrogen bonding is only capable of pulling in 4 or 5 carbons for each of those groups that hydrogen bond, okay? So by the time we get to pentanol, it is not very soluble in water. However, by adding a second alcohol to that thing, to that chain, we have approximately the same molecular weight. We have 2 things hydrogen bonding. Therefore, it changes the boiling point again, making it even higher because we have 2 parts that can hydrogen bond per atom. And it again becomes infinitely soluble in water again. Now, if we compare that with hexane, which is approximately the same weight, it has a much, much lower boiling point because it only has those dispersion forces holding it together. And it's completely insoluble water because it doesn't have any hydrogen bonding. Okay, so now that we know what hydrogen bonds, we also need to think about alcohols as acids and bases. And the first thing we want to do is compare it to water. So water has 2 lone pairs and 2 hydrogens that can be acidic. Alcohols tend to have that 2 lone pairs on the oxygen and 1 hydrogen that can act as an acidic hydrogen. And if we look at the pKa's, the pKa of methanol is just slightly below that of water at about 15.5. So they're very comparable to water. Ethanol is just slightly above it, about 15.9. And so that, the alcohols all range in this area here. They can act as acids because the proton here can be removed, giving you an anion stabilized on that electronegative oxygen. Okay. Now, what this means, because the pKa is approximately the same as water, we actually have the same pH as pure water, and because it has approximately the same acidity. Okay, now let's compare some pKa values to get it kind of where it is in our series here. Hydrogen chloride, of course, is a strong acid and has a pKa of -7. We go to our weaker organic acid, and that's acetic acid, which is a pKa about 4.8. Methanol, water, and ethanol are right in that middle band, about 15. And then, of course, we go to, as we add additional carbons to the chain, the acidity goes down. It becomes slightly weaker acids because that hydrogen is having to pull more and more organic material into solution. Okay, now that we know that ethanol can act as a base, act as an acid, it can also, it can also act as a base like water can, okay? So in the case here, we have ethanol, the lone pair on the oxygen here, can accept a proton from an acid to make a strong acid, the oxonium ion, so that all alcohols can act as Bronsted-Lowry bases as well as Lewis bases because it has that lone pair to accept either a proton or a incoming electrophile. Okay. In contrast, when we move to ethers, an ether has the carbon-oxygen-carbon bond. So we've removed that hydrogen. By removing that hydrogen and adding another carbon bond, we still have a polar bond between the carbon and the oxygen, but we no longer have the group that will do a hydrogen bonding. Okay, so what this means is we have two polar bonds that don't cancel each other out because they're 110 degrees apart. Therefore, we now have a polar molecule. If we look at our structure of our ether here, we have 2 lone pairs electronically holding those 2 other groups out. We have electron density being pulled in toward the oxygen. So we have a net dipole of the ether functionality to give us an ability to make that polar covalent bond and a polar molecule. When we have polar molecules like that, we have another interaction that we can call a dipole interaction, where the negative side of a dipole is attracted to the positive side of the dipole, and that gives us an additional interaction above the dispersion forces, but it's weaker than the hydrogen bonding. So we're going to see less of an impact on the physical properties compared with that of those that can hydrogen bond. So let's look at a table here. Now, if we compare molecular weights again to different compounds, ethanol and dimethyl ether have approximately the same molecular weight here, but they have about 100-degree boiling difference. Okay. Now, if we think about that, that has everything to do with the fact that ethanol can hydrogen bond and the diethyl ether can only dipole-dipole bond. Okay, that loss of hydrogen bonding decreases its boiling point, but it also decreases its solubility in water. A dipole interaction with a hydrogen bonding still is an interaction, but it's not as strong as the hydrogen bond interaction, and therefore it decreases solubility in water as well. So that losing of the hydrogen bonding, we lose boiling point and we lose solubility in water. So let's add a couple more carbons to the system so they're about the same molecular weight again. Again, we see almost 100-degree difference in boiling point going from something that can hydrogen bond to something that only has dipole-dipole interactions. And we have approximately the same solubility in water at this point. And then as we go higher and higher into the system, we see that the boiling points start to diminish compared with equal molecular weights of the material, and their solubility also decreases in water. Okay, so I said that the dipole can hydrogen bond with other things. And so if we have something like water hydrogen bonds, that's its major bonding aspect to it. Our ether only has that dipole interaction. Now, ethers are slightly soluble in water because the dipole will interact with the hydrogen bond, helping donate some of that hydrogen to that partially negative dipole and allow some interaction, but the actual ether itself does not hydrogen bond to the water. The water is hydrogen bonding to the ether. In the case of alcohol, alcohols are hydrogen bonding to each other, therefore increasing the boiling point even more. So this is a weaker interaction, therefore it has less impact on the solubility than the hydrogen bonding. Okay, so, and just to drive this home, ethanol and diethyl ether are basically constitutional isomers. They have exactly the same molecular weight. The ethanol has hydrogen bonding and has a significantly higher boiling point, 100 degrees higher. The dimethyl ether, while it has a higher boiling point than propane, which is approximately the same molecular weight, it does have a polar nature to it. The molecule itself is polar, and therefore it does have dipole-dipole interactions, which accounts for its increased boiling point from propane, but its decreased boiling point from ethanol, which hydrogen bonds. Okay, the last functional group we want to talk about is the thiol. And thiol is similar to that of an alcohol, where you have an electronegative atom bonded to a hydrogen here. Their most known characteristic is the fact that they have what we call stench. They smell very bad, and it's partly designed because the human nose was developed over time to have an aversion to things with sulfury smells to them because they tend to indicate things that are poisonous to the human body. So we can sense these small amounts of sulfur in parts per billion in the air. And so we can actually use that to our advantage because things like natural gas and propane actually have no smell. And so it could easily build up into an explosive mixture before we would ever know that there's anything there. So what they do is they add trace amounts of either this T-butyl mercaptan or the isopropyl mercaptan to that natural gas so that we can smell that little bit of sulfur compound in parts per million, and that's before we have an explosive mixture of the natural gas and air. Therefore, we're using it as a safety thing. Where we've developed this safety protocol over time to be able to smell these in little small doses, and now we're using that again to help us be safe from natural gas explosions. Okay, now you might think, oh, so the sulfur is kind of like oxygen. It can hydrogen bond too. But it actually doesn't, because the electronegativity difference between sulfur and hydrogen is only 0.4. The electronegativity of carbon is 2.5, and the electronegativity of hydrogen is 2.1, meaning they have approximately the same polarity as a carbon-hydrogen bond. And as such, it has a very low ability to hydrogen bond. That's not a polar enough bond for it to hydrogen bond. And we can see this to be true because they are less soluble in water, and they have lower boiling points when compared with molecular weight. For example, if we look here at methane thiol and compare it to methanol, we have a 60-degree temperature difference here. There's some interactions, there's some polar interactions there, but it doesn't hydrogen bond anywhere near as strongly as the alcohol functionality. Okay, and then just by adding extra carbons, we do see an increase in boiling points, but they are not as dramatic as the increase in boiling points we see with the alcohols. So they hydrogen bond less than OH groups. And the last thing we need to think about is that because thiols can form more stable anions because they are a larger group, they actually are more acidic than their oxygen counterparts, okay? So the sulfur group is a bigger group, therefore it can just disperse that negative charge around that makes it a stronger acid. And if we measure the pKa of ethanol, we get a 15.9 just above water. And if we measure the pKa of thioethanol or mercaptoethane, we have an 8.5, okay? So what that also means is because it's a stronger acid, it can more easily be deprotonated by salts by bases to create a salt of the thio compound. When we create a salt of the thio compound, like this compound here, we actually turn it into a strong nucleophile, and we can use it in many chemical reactions.